All right, welcome to VSEPR kind of expanded. We're going to go past molecular geometry and move into something called electron domain geometry. When we talk about VSEPR, we kind of talk about both of these two things. Um, Now, normally we focus on molecular geometry because it tells you a little bit more than electron domain geometry, but electron domain geometry has its uses. To give the quick, short kind of answer to any question you may have. All of these right here are going to be tetrahedrals. All of these right here are going to be trigonal, planar, and this is still going to be linear. And that's just kind of the breakdown. Electron domain geometry is not as specific as molecular geometry because electron domain geometry specifically only talks about kind of the electron sets. It's talking about the total bonded pairs and lone pairs of electrons. So some examples might be, for example, let's see, CH4, which is going to be methane, and ammonia, NH3. CH4 we can draw quite simply as this, and NH3 will be very similar as CH4. However, the main difference being we have a lone pair of electrons at the top versus a bonded pair of electrons. Now, the thing is, when we're looking at electron domain geometry, both of these are still tetrahedral. Because in the very vague sense, if we look at any given atom here, we kind of have the center, and we have some electrons up here, electrons over here, electrons over here, and electrons over here, which kind of make this vague tetrahedral shape. Um, Especially when you're looking at this more in 3 dimensions. So electron domain geometry doesn't actually focus on the individual bonds, more just the domains of electrons. It's kind of self-explanatory. So in addition to explaining that concept, I'm going to explain one other just small concept here, which is how bond angles can kind of be shifted. Um, Now, that's a little more kind of subtle, but I'm going to go through it anyways. Generally, we say the bond angle in a tetrahedral, sorry, is about 109.5. Now, however, in ammonia, this is actually going to be a little less than 109.5 degrees. And that's because these electrons exhibit a repulsive force. Hence, in VSEPR, valence show electron pair repulsion. These lone pairs of electrons are going to repel and kind of push these bonds a little closer together. And the more electron pairs, specifically the more lone pairs around, oof, let me just go ahead and rewrite that one. The more lone pairs around a central atom, the smaller the bond angle. And that's just kind of the way that it is. And the whole reason for that is when we have a bond of ammonia, for example, and we look at these electrons, ammonia, nitrogen's own lone pair are held very tightly to it. Meanwhile, these shared electrons between the hydrogen and the nitrogen, these aren't shared so tightly. These are, in fact, a little further away from the nitrogen than the bonded pair. I don't mean to say that these are closer to the hydrogen. That's a discussion for another video. But what I mean to say is that in the grand scheme of things, Now that I've said it's going to bug me, these hydrogens would be further away than the nitrogen from the bonded pair, and that's just due to electronegativity. But I digress. These electrons right here in the bonds are technically further away from the nitrogen. And because they're further away from the nitrogen, and in fact, these are actually further away from each other than they are from these lone pairs right here. If we were to actually measure the distance between them, I'm going to go ahead and get the right color for that. The distance of the green between the lone pair is actually that green line is much smaller. And because of this, the lone pair are closer than the bond. And as electrostatic interactions or Coulombic forces or electrostatic forces, three names for the same thing, dictate if the distance is smaller, the force exhibited is larger. And therefore, they're going to push those angles together. They're going to exhibit more of a repulsive force, pushing those bonds closer together. So that's that whole side. The last thing I was going to talk about is drawing these models right here. It's so important to be able to draw these Lewis diagrams. And while doing it quickly takes practice, it's good to kind of work on the basics. So we're going to actually practice 3 of them right now. We're going to practice ClO2 minus. This is a chlorite polyatomic ion. We are also going to practice ammonia, which is NH4 plus. And then we're going to practice PO3 2, and that's going to be phosphate, or sorry, phosphite. That's going to be PO3 2 minus. So pause it right here, go ahead and find them on your own, and now I'm going to go ahead and actually dictate how I personally go through them. So I'm going to start with chlorite. I'm going to start with, usually in these polyatomic ions, this first one's going to be the center. Oxygens, using their weird oxygen rule, and hydrogens just tend to be on the outside around the central atom. So it's a good idea to just kind of slap those in the middle and go ahead and draw their Lewis dot diagrams. Now, I also know that oxygen can always use its rule, which once again is that oxygen will often, especially in polyatomic ions, take their electron, and I'm actually just going to do it, scooch it over next to one of their other ones, kind of creating like this weird, vague, empty spot, and then just go ahead and latch on and create a covalent bond without actually sharing any of its own. And so we can kind of just do that in our diagram, which is what I'm going to do. Go ahead and erase these. And I'm going to just draw kind of a line. Oops. I'm going to just kind of draw a line to show that they're going to bond. And then lastly, you might say, Mr. Garcia, the octet rule is not filled. Even with this, we still kind of have this awkward lone electron right here, but that's where this minus comes in. We can get a charge, especially a negative charge, by adding one electron. This actually means that we are gaining one electron. So I'm just going to slap that little electron right here, and I'll fill it in so you know it's specifically that one. The last thing I'm going to do is go ahead and redraw my structure, just clean it up a little. I know chlorine has one bond to each oxygen, which will still hold all 6 of its original valence electrons. Remember, oxygen is not contributing any of its own. And then to fill it out, chlorine will look like that. Next, we have ammonia. Again, I'm going to start with nitrogen just smack dab in the middle and draw its Lewis dot diagram. And we have 4 hydrogens, 1, 2, 3, and 4. Usually when we have 4, it's kind of safe to assume that they're just going to go around in kind of a tetrahedral fashion. And they will proceed to bond. And you might notice that we have a problem, actually. We have a full set right there, and hydrogen still wants to bond. But that's okay, because we have this plus right here at the top. And the way we get a positive charge is to lose 1 electron. So I'm actually just going to go ahead and steal. I'm going to steal that electron away. And I'll even go ahead and erase it to get it out of here. And then hydrogen can go ahead and bond, and I'll clean up my picture a little. And lastly, we have PO3 minus. So I'm going to go ahead and give this one a shot again. P1, 2, 3, 4, 5. And we actually have a 2 minus charge, which means we're going to, instead of gaining 1 electron, we're going to gain 2 electrons that we can just kind of throw in there pretty much wherever we want. 6, oxygen, 1, 2, 3, 6, 4, 5, and 6. So we need to fit 3 oxygens, and we have a couple electrons we can play around with. Now, this one gets just a bit tough because I can't just single bond willy-nilly. I can't just kind of throw it around, throw it around, throw it around, because while phosphate's happy, if I throw in 1 extra electron here and here, we're still leaving this oxygen kind of messed up. And so this becomes a bit more difficult of a situation where we are going to have to start analyzing some patterns. But that's okay. This is what I like about covalent bonding. It's kind of this weird puzzle that we get to fill. But for me, the option kind of becomes clear. I know oxygen will always bend to its own rule if it can, and that's kind of like a fallback I can count on. So what I went ahead is just kind of filled 1 oxygen. And I'll go ahead and then just drop one of those spare electrons, maybe right there. See what happens. If we do that, we can scooch this one over here. And as we continue this, I actually realize I made a mistake, so I'm going to just go back. Phosphite isn't 2 minus, it's actually 3 minus. That means we get 3 electrons to play with, which kind of just opens it up to say, well, we could have changed it before and just done this whole thing. Well, we just simultaneously add our 3 electrons here, and oxygen shares its own electron. So let's go ahead and clean this up. I'm actually just going to erase it and start over. E, 1, 2, 3, 4, 5. Oxygen, oxygen, oxygen. And you'll notice this time around, I already drew the electrons shifted over. So we can just add our 3 electrons in here, and oxygen does its thing. Therefore, clean it up, and it looks like this. Now, the last thing that we have to do for all 3 of these diagrams before you yell at the screen is these are Lewis structures of charged ions, specifically polyatomic ions. So when you do a Lewis structure of a charged polyatomic ion, you must include the charge in your diagram. And so that's it. And the interesting thing about this is our electron domain is all going to be tetrahedral. However, both that one and this one are not going to be a tetrahedral molecular geometry. This one's going to be trigonal, pyramidal, and this one's going to be bent. All right. Well, hopefully this helps. The notes that I did right here are going to be in the description. Have a great night.